Continuing our discussion of a 4-electron pair case, let's take an example where the number of bonding pairs is 2 and the number of non-bonding pairs is also 2. So a 4-electron pair case, 2 bonding, 2 non-bonding. And a typical example of this category would be water, H2O. So that's water. And the usual practice is to calculate the total number of valence electrons in this molecule. And the valence electrons would be 6 from oxygen, because oxygen is located in group 6A, so it has 6 valence electrons. And there are 2 hydrogen atoms, each of them has 1 valence electron. So 1 by 2, and the total number of valence electrons is 8. If you divide 8 by 2, you get 4 electron pairs. So there are 8 valence electrons total in water and 4 electron pairs. To draw a Lewis structure, we need first to draw the central atom, which is oxygen. So that's oxygen. And the surrounding hydrogen atom, so that's 1, and that is 2. And then you draw single bonds between the central atom and the surrounding atoms. So that's the oxygen-hydrogen bond, and that's the other oxygen-hydrogen bond. And now we need to satisfy the duet rule or the octet rule in general for surrounding atoms. And the surrounding atoms in this case are hydrogen. So we need to make sure that these hydrogen atoms satisfy the duet rule. In other words, they should be surrounded by 2 electrons. If you look at this hydrogen, it has a bond with oxygen, so it is surrounded by 2. This hydrogen is the same. It is surrounded by 2 electrons. Therefore, both of these hydrogen atoms obey or satisfy the duet rule, which is again according to valency rules. But the central oxygen atom is surrounded by only 4 so far, and there are 4 valence electrons anyway in this tentative Lewis structure, but we had 8 before. So we need to place 4 electrons, 4 more, or 2 pairs if you like, on the central oxygen atom. So that's 1 pair, and that's another. So these 4 electrons, or these pairs, are in the form of non-bonding pairs or lone pairs. If you double check the satisfaction of the octet rule by oxygen in this Lewis structure, you would find that it is surrounded by 8, so that's reasonable. So there are 8 electrons used in this structure and 4 electron pairs. 2 of them are bonding, and whereas the other 2 are non-bonding or lone pairs. The orbital shape or the molecular shape is still tetrahedral, following this general model. Okay, so the orbital shape, we can write that down. It is tetrahedral, but the molecular shape is not tetrahedral. Now that's because not all of these 4 electron pairs are bonding. 2 of them are bonding, whereas the other 2 are non-bonding. So maybe we should take 2 bonds off, and if we do that, we get something like that. So that's like a lone pair. That's another. Now if you look at this shape, okay, this is actually bent. So the molecular shape is bent, or if you turn it upside down, it is V-shape. So the molecular shape of water, in this case, is V-shape or bent, and that's because not all electron pairs are bonding. So the molecular shape is V-shape or bent. What about bond angles? Well, bond angles again are not 109.5, and that's because of the presence of 2 lone pairs now. So now we have to take into account lone pair repulsions and lone pair bonding repulsions, and of course bonding repulsions. This angle will squeeze even more than the previous ammonia case. Now this bond angle will always be less than 109.5, as it should scientifically be represented. So it is less than 109.5, the bond angle. So that's a general representation. It is found experimentally in the case of water to be 104.5. So in conclusion then, in a 4 electron pair case where 2 pairs are bonding and 2 are non-bonding, the orbital shape or the molecular shape, the orbital shape or the overall arrangement of electron pairs is tetrahedral, whereas the molecular shape is V-shape or bent. The bond angle in this case is better represented or scientifically represented to be less than 09.5 to account for the 2 lone pairs present around the central atom.